In this video, we're going to be starting to talk about reactions we see with alkynes. There are a number of reactions that we can see with alkynes, just like a number of reactions we can see with alkenes. So this is going to be split up into two different videos. In this one, we're going to be looking at hydrogenation. So if we remember from reactions with alkenes, that's going to be addition of H2. We're going to see addition of HX, hydrohalogenation, and we're going to be seeing addition of X2, so halogenation. So hydrogenation is what we're going to be talking about first. So this is addition of H2 across a double or a triple bond. So if we remember, we saw that if we take an alkene and we add H2 on some kind of platinum, palladium, rhodium, rhenium catalyst, any kind of metal catalyst, we will have reduction to the alkane. And it turns out that if we have H2 on platinum or palladium, so that would be the same reaction conditions, we will end up with the same product. So H2 will continue adding to an alkyne to reduce it all the way to the alkane, where we've added now 2 H's at each position. But sometimes we don't want to do this. Sometimes we want to stop at the alkene. So what if we want to go from the alkyne to the alkene? And the way we can do the alkyne to the alkene is by using what's called a poisoned catalyst. So a poisoned catalyst has additives added to it, so there's fewer active sites that the catalyst can actually hydrogenate the compound. So essentially we have a less reactive catalyst. So we can add H2 on what's called Lindlar's. The one that's most commonly used is Lindlar's catalyst. It's a I believe it's platinum poisoned with quinoline, and that will take the alkyne down to the alkene. What is interesting to note is if we have an internal alkyne and we add H2 on Lindlar's catalyst, it will only take it to the cis alkene. So this is only cis alkenes, and that's because similar to the mechanism, the syn addition of H2 on an alkene, we are going to have syn addition of H2 on an alkyne as well. But how can we stop at if instead of the cis alkene, we want the trans alkene? So say we wanted to go from this internal alkyne to the trans alkene, and this requires a totally different set of conditions. This is what's called a metal ammonia reduction. So metal ammonia reduction is going to be taking something like sodium or lithium or potassium metal, adding it in liquid ammonia, and that will take the alkyne to the trans alkene. So this is selective for the trans alkene. So let's look at the mechanism, and this goes through a radical mechanism, which we'll see in a later chapter. But it's a good introduction to see this radical mechanism now. So say we have a 2-butyne, and we're doing the metal ammonia reduction. So metallic bonds, remember, they're carriers of electrons. So we can have free electrons, and notice I'm using single-headed arrows here to indicate the flow of one electron. So we are going to take this down to the trans alkenyl radical. So we generate the radical anion. So there we have the radical anion. This is going to pluck a proton off of NH3. We now have a stronger base than NH3, so we're going to pluck a proton off of NH3. We lose NH2, which will, and this loses Na+. We'll have that salt form. So we now are at the trans alkenyl radical. That alkenyl radical is going to have addition of another electron with the sodium ions, and I'm just using sodium. This could be lithium, potassium, cesium, whatever kind of metal you're using. That will once again result in loss of Na+, and forming the anion again, which will then pluck another proton off of ammonia to form the selectively the trans alkene. And if you're tracking the counter ions, the counterbalance in this equation, we end up with 2 equivalents of NaNH2 or MNH2, depending on what metal you used. So this is the hydrogenation. So just as a summary, if we're looking at this 1-butyne, if we add just H2 on platinum, we will get down to the alkane. If we do H2 on a poisoned metal surface like Lindlar's catalyst, we will end up with the cis-alkene. And if we do a metal ammonia reduction, so say sodium metal and NH3 liquid, we end up with the trans-alkene. So 3 different ways we can do hydrogenation of alkenes, or alkynes rather. So let's look at our next reaction setup. So this is going to be addition of HX to an alkyne. So if we remember from a previous chapter, if we take an alkene and we add HX to that alkene, we'll have addition of X Markovnikov to the double bond. So this is a Markovnikov addition, meaning that it goes to the more substituted side. So we have that secondary alkyl halide instead of the primary alkyl halide. It turns out that alkynes will do a similar addition if we add HX. And add the X to the Markovnikov position. So we've added the Markovnikov, making that internal halide instead of that terminal halide. But just as we saw with hydrogenation, it doesn't have to stop there. If we do this in non-stoichiometric amounts or excess amounts of HX, you can get a second Markovnikov addition. So you end up with the geminal dihalide. So this is geminal. To the alkyne to result in 2 additions of HX, double hydrohalogenation to the triple bond to get all the way from the alkyne to the geminal dihalide. This is a Markovnikov addition. If we wanted anti-Markovnikov addition, we can simply do this in the presence of peroxide, so ROOR. That will add the X to the terminal position, that anti-Markovnikov position. And if we do this one more time, or we're in excess HX, this will add the geminal dihalide to the terminal anti-Markovnikov position. So we can control the regiochemistry depending on whether we do this in standard conditions or in the presence of peroxides. And that's just like we saw with the addition of HX with or without peroxides to an alkene. The final reaction I want to talk about for alkynes is the addition of X2. So if we're looking at an alkene and we add X2, that's going to add to the double bond. And remember, it's going to add in a anti arrangement, or we could call it trans if there's no other stereochemical centers involved. And we see that if we have an internal alkyne, we're also going to add in a trans arrangement. So these are going to add trans on the double bond. And like we saw with the HX addition, if we are in excess X2 or non-stoichiometric amounts, we can add 2 equivalents of X2 to an alkyne and form the double geminal dihalide. It starts out trans, just like we have the trans addition of a X2 on a double bond, but we will have the trans configuration and add twice 2 equivalents of X2 across that triple bond.